Hello, everyone. In this example, we'll be talking about stress concentrations. So the idea here is that generally in a cross-sectional beam like this, you have an average stress that propagates through the entire cross-section. But when you add additional features, like in this case, you have a notch on either side as well as a hole, it amplifies this stress, causing a peak stress that is a function of the geometry of these additional features. And if you've already watched the lecture, you would have seen that the maximum stress or the peak stress is equal to some factor which we call the stress concentration factor. And T here means that this is in static loading. So in our case, we have a beam that is statically loaded axially with a force of 65,000 newtons. So it's basically the stress concentration factor multiplied by the nominal stress. And the nominal stress here basically is your P over A if it's axial, or your MC over I if it's a bending moment, or your T rho over J if it's torsional. And sigma max here is basically your maximum stress due to the stress concentrations. And if your maximum stress is greater than your yield strength, then that stress will cause yielding. So let's get into this problem. Now, KT, oh yeah, and KT, of course, are your stress concentration factors that you get depending on the geometry of your features from the textbook. So in our case, I've pulled out the two plots that we need. So we have figure 4.39 and figure 4.4, in which you statically load just a beam with a notch, and in the other one, we're going to use this one right over here, where you statically or axially load another beam with a hole. Now, what's important is when you're looking at these plots to pull out your stress concentration factor, you need to realize that a certain beam, so in our example, we have a rectangular beam with notches on either side, it can be loaded axially as well as with a bending moment in this case. So that's why 4.39b is axially loaded, but 4.39a in the textbook is in bending. So just a quick look at your textbook. So this is what I mean. The top plot talks about, or rather gives you the stress concentration factors if it's loaded in bending, and the other one if it's loaded in tension. So make sure that you pick up the right plot depending on what type of loading you have. Okay, so again, the prompt is, what is the value of the maximum stress at both the hole and the notch? Now, because we have two different plots, right, and the way we have our equation written out, we need to solve for a sigma max at the hole and a sigma max at the notch. And there's no way of combining these two because these are two separate geometries. So what we're going to do first is figure out what sigma nominal is, which is our nominal stress. So that's always your first step when calculating your maximum stress. So if you have features like this, you might end up starting off with loads, and then you convert that to a stress, and then you have to apply the stress concentration factor. So there's a kind of a procedure. So first thing to always do is solve for the nominal stress. So sigma nominal, now in our case, it's an axial load. So we have P over A, right? P over here is your 65,000. And the area, it's very important to mention, is that the area is the area of material at the discontinuity. Or in other words, where your additional feature, like in our case, the notch or the hole, is added, right? And we only need to calculate one sigma nominal because at both the features, exist at the same point or along the same line on the beam, where the cross section is, in our case, uniform. So what we need to do is figure out what that area is, and we need to find out how much of that cross-sectional area is actually has material. So for our axial load, what's important is that the stress is, or the area is perpendicular to the load. So in this case, let's take this section here. Oops. So section AA, right? And let's look at it. So section AA would look something like this. Where here is your first notch, this is your second notch, and this is the hole. And if you and we're only interested in this area right here, because this is where we have material. So this is the area in the beam that will actually carry all the load, right? So it looks like two rectangles basically. And we also need to know what the thickness of the beam is. So we have this as 25 millimeters. Again, all dimensions are in millimeters. And this is 200. This is 15. This is 15. And the diameter of the hole is 30 millimeters. So we need to, using these dimensions, we need to calculate the area of the two rectangles we have. So that's going to be, again, it's 25 for both the rectangles, the thickness, and then the width will be 200 minus 2 times 15 minus 30. Right? So it's very important that even though it's an average stress, we need to calculate it with the area in which we have material present. So computing that, the nominal stress is equal to 18.57 megapascals. All right. So now that we have the nominal stress, and this applies to that point that has both the hole and the notch, what we can do next is calculate the maximum stress. And we'll talk about why in this case we can separate them and treat them individually, and in cases where we can't do that, and where we will need additional plots in order to do these calculations. So, no, that's not what I wanted. So the maximum stress so sigma max is equal to KT times sigma nominal. So the first thing we'll look at is the notch. Right? So sigma max notch is equal to KT due to the notch times sigma nominal. Again, if these holes were placed, if the hole was placed at a different location than the notches, and this hole over here was filled, then you would have two different sigma nominals. One over here, that would just be the 200 divided minus the diameter of the hole, and the notch and the sigma nominal for the notch would be 200 minus the 2 radii of the notches. Okay. So we need KT for the notch, right? So let's look at the plot in figure 4.39. And it seems like we need to know two quantities before we can decide or find the value for KT. So one is R over H, which is the radius of the notch divided by the distance between the two notches. And the other one is capital H over H, which is the full length of the beam minus little h again, which is the distance between the two notches. So let's calculate those values. So for the notch, we need R over H, which is 15 millimeters minus 200 minus 2 times 15, right? So that's 15 over 170, which is 0.09. And then similarly, we need H over H, which is 200. And again, H we calculated as 170, which gives us 1.2, roughly. So now we can go back into figure 4.39. So we have 0.09, which is here, right? And we have 1.2, which sits in between these two lines here. We're closer to the bottom one, so we'll have something. So we can, you don't have to be this precise. You can just eyeball it. So we know it's going to be somewhere here. So I'm going to take 2.45. Now you could take 2.5, 2.4 to some extent, and that'll be fine. We're not too strict on what value you pick. But if you pick 2.6, yeah, I would try to stay relatively below 2.6 and above 2.4. Because if you pick like 2.2, that doesn't make sense. 2.3 also doesn't make sense. So, try to stay in between the lines, but closer to 1.15. So 2.45 is a decent value. So based on that, KT for the notch is 2.45. So the maximum stress due to the notch is equal to 2.45 multiplied by the nominal stress, which is 18.57, and that gives us sigma max at the notch equal to 45.5 megapascals. All right. And then we can do the same with the hole. So we have again sigma max at the hole is equal to KT, the stress concentration factor due to the hole, times sigma nominal. And let's look at the plot and see what values we need. So this is a simple plot. We only need to calculate d over b, and d over b here is the diameter, or the ratio of the diameter of the hole and the length or the full width of the beam. So that's all we need, yeah. So d over b is 30 divided by 200, which is 0.15. So going back in the plot, we have 0.15, which is this line over here, and that's almost exactly 2.5. So in the exam, we will try to give you values or that will end up in ratios that give you a more clearer picture. Like in this case, it's 2.5. If that happens and you pick like 2.8 or 1.75, then we'll mark it wrong. So, get some practice trying to read values off the plot. Okay, so this is 2.5. So d over b gives us the KT of the hole equal to 2.5. And again, this is figure 4.40, and this was figure 4.39. So sigma max at the hole is equal to 2.5 times the nominal stress, 18.57. So sigma max at the hole is equal to 46.4 megapascals. So this is all that's required in the problem, right? We just need to calculate the maximum stress due to each. But I want to take it a step further and discuss a little bit about why we were able to separate these two out and what is a major assumption we've made over here. So I'm going to redraw okay, right? So we have this beam right here with these features in it. So we can say that this is a combination of a beam with just a notch and a beam with just a hole, right? And if we were to look at the stress concentrations due to each of them, let's say, so everything in here is in tension, everything here is in compression, and we have everything in tension. So we're going to start off at our nominal stress, right? And as we, and let me draw some lines across here, just to show where the feature is. And this is because we're loaded axially, right? So that means we have a load this way. So the stress is going to start from some nominal value and peak near the discontinuity this way. So this is basically our stress distribution, right? Where this value here is approximately sigma nominal, and this peak value here is going to be sigma max. Similarly, for the beam with just a hole, we would have our lines going this way, and then we'll split it in compression or tension. This is just basically you drawing positive values versus negative values, right? If your beam was in compression, then like for the first one, it would look something like this. That's all. It's just negative versus positive, and this would be negative sigma max, right? So nothing too complicated here. Oops. All right. And in this case, it would start off with some maximum value over here, some minimum value here, up to a maximum value as it approaches the hole. And again, this is our stress concentration, or a stress distribution, rather, where this value here can be approximated to be sigma nominal, and this value here would be your sigma max. And this is for the hole, and this one here is for the notch. Now, what does it look like when I combine these two stress distributions onto this guy right here? They will overlap. If the hole and the notches are close enough, these will overlap, and the stress concentration factors that we use to calculate them will not be applicable anymore. So you could, so it would probably look something like, so this was close enough, right? This would start off at some value and then peak here. But at the same time, this is already approaching its discontinuity here. So it would probably do something like this and then go up this way. And as a result of this, compressed nature in the width, we can't use KT plus K and KT pole plus KT notch or some other factor. What we need instead is a physical plot which has a beam loaded in this fashion with a hole in it and its own respective lines, right? And then you'll have this dimension in the like R over H, and then you'll have the D over B, and then your KT would be on the Y. If you don't have a specific plot, then you can make this assumption, and this is a very important assumption that I should have made in the beginning, is that the hole and the notch are far enough such that the stress distributions don't overlap. So what would the stress distribution look like in this case? So if we assume that they're far enough, so for that I'll have to draw an unrealistic diagram. And again, we won't trick you or give you any additional plots. Just make yourself familiar with any of the plots you already have in the textbook, and that should be enough. Um, and if we do give you something like this, where both the features are in the same line, then you can make the assumption that they're far enough that their stress distributions don't overlap or they don't affect each other such that the stress concentration factor increases more than what you've pulled out of the plots. So in this case, it would be, then let me draw my line here. Both are in tension, so they would be on this side of the line. And we have this line that goes across this way, this way, this way, and this way. So it would look something like this. So they're far enough such that you have this region over here that makes sure that the two stress distributions don't overlap. And this value here is your 45.5 megapascals, and this value here or here is your 46.4. And 45.5 is that value. No, sorry. These two lines are 46.4 megapascals, and this is your 45.5.